So welcome everybody to part 2 of the Michelson Postdoctoral Prize lecture series of this week. So with our winner Ben Lyman, who you met yesterday. So just a reminder of the other events. So on Thursday during the normal colloquium time, we have the prize presentation and colloquium, and we have a reception tomorrow here at 4:30. And also after the talk today, we'll go for lunch, a free lunch. If anyone wants to come and join, we'll just go to the cafeteria across the street and get stuff. And then there's also opportunities throughout the week to meet Ben. He'll be here all week, so let me know. So with that, I'll turn it over to Ben, and today's topic is compact objects as dark matter.
All right, thank you, Kurt. If you weren't able to join for yesterday's talk, I do want to just remind everybody that what gets me up in the morning is dark matter and figuring out what dark matter is. So although there is lots that you can do with compact objects, they are fascinating for many reasons, I want to focus for today on compact objects as a dark matter candidate. And specifically, I want to argue that we are actually very close to being able to make a definitive statement about whether dark matter is composed of compact objects, at least of black holes, possibly of compact objects more generally. So that's why I call this the Endgame. Just to remind you of where we stand. I showed you this slice yesterday in the talk, the dark matter parameter space in mass. There's 90 orders of magnitude here. Much of our effort in the particle physics community over the last few decades has been focused on that red band where WIMPs live. And yesterday I was focused on telling you about that yellow band, light dark matter, and how we can get to that in the next 5 to 10 years. For today, I want to focus on the other end of the spectrum. I want to focus on compact objects, which I distinguish from elementary particles in that they are too heavy to be elementary particles. So there's really a line at the Planck scale, which is where that blue region starts, where it no longer makes sense to have a single fundamental particle as the dark matter candidate. It must be a composite or some other kind of object. Now there are lots of things that could live in that blue band. There are lots of different kinds of composites or compact objects, macros, all kinds of different phenomenology. I want to focus for most of this talk on primordial black holes, which are arguably the most minimal dark matter candidate that you could think of. So first of all, what are primordial black holes? These are black holes that would be produced in the early universe when we know that dark matter had to be produced. So since they're produced long before stars, we're talking about black holes that are produced by other processes directly in the cosmological environment at early times. So these black holes can span lots of different masses. They don't have to be in the sort of solar mass to many solar masses regime where we've already seen black holes. In principle, they can tell us a lot about the conditions of the early universe. They're really exciting objects for a lot of reasons. But right now what I want to highlight is that they are an ideal dark matter candidate. They are cold. They're perfectly non-relativistic. They're not moving fast. They are dark. They interact only by gravity. Even if they get a little bit charged, it's almost entirely gravity. And they behave exactly like dust. They're just like matter. Now, you might kind of object. I mean, we think about dark matter often as a kind of a fluid, as a diffuse kind of gas. So can you really make a gas out of big black holes? And the answer, as any simulator knows, is absolutely yes, because the particles that we use in all the simulations that make beautiful pictures are actually much heavier than primordial black holes would be as a dark matter candidate. So everything that we know about dark matter is perfectly consistent with having massive, compact objects instead of small elementary particles. Now, I am going to think about primordial black holes because they're inherently exciting and they connect to a lot of early universe physics, but they're also a useful proxy for compact objects as dark matter generally, because a lot of the phenomenology that one wants to access with primordial black holes can also be accessed with other kinds of compact objects. So you might think, for example, about even things that involve a dark matter particle. For example, boson stars, where you have little clumps of dark matter that form in the early universe. They behave essentially like these compact objects gravitationally. So studying primordial black holes is a great way to understand, basically, is the dark matter really diffuse at small scales, or is it in some way granular? Now that said, I do want to say a few words about the actual physics that you can probe with primordial black holes, because there's actually a lot of really interesting early universe physics that would produce them. So there's a few classes of things that can give you primordial black holes in the amount that you might expect for dark matter. Just to list a few. what I call the direct way of making primordial black holes is by just having enhanced primordial fluctuations, right? So the density distribution in the universe comes from initial fluctuations at very, very early times. If that initial spectrum of fluctuations has a peak at small scales, then you might have patches collapse on small scales and give you black holes. So this is directly connected to the physics of inflation. If you tune the parameters of an inflaton, you can create a scenario with primordial black holes. There's all kinds of other high-density physics that can make black holes, whether they're all the dark matter or just a tiny fraction. So basically anything that gives you a very high energy density can make black holes. So things like topological defects, strings, if you have phase transitions, even if those don't directly make black holes, they can assist the formation of primordial black holes. So they're an important part of the story. And the last category is actually from other dark matter particles. So does a primordial black hole dark matter scenario require additional particles? Well, arguably no, as long as you accept that the inflaton is part of the set of particles you would already accept. But if you have a scenario with a complicated dark sector, let's say, it's actually very possible to form primordial black holes at early times from those particles, if they can cool and collapse and make black holes. So those are a few kinds of physics that you can access with primordial black holes, and that can give you black holes as a dark matter candidate. So what's the status now of primordial black holes as a dark matter candidate? This plot is close to my heart because I've worked on many pieces of it. But this basically shows the constraints that we have today on primordial black holes as a dark matter candidate, assuming that all of the black holes are at the same mass. They don't have to be. If you deviate from that, these move around a little bit, but actually you can bound the extent to which these curves move around. So first I want to point out the top line on this plot. That is 100% of the dark matter. So in order for black holes to account for the dark matter, they need to make it all the way up to the top of this plot. Now, you'll notice there is a gap in this plot where the dark matter can actually do that, between masses of about 10 to the 17 grams up to about 10 to the 22 grams. So in principle, there are some other regions that are interesting here. So the bounds at low masses, those actually come from evaporation, where we don't really understand the physics that well as you get down to very low masses. So there have been various suggestions over the years that maybe evaporation, as black holes Hawking radiate, that actually doesn't go all the way. They stop at some point, in which case you might have smaller black holes as dark matter, in principle all the way down to the Planck scale. There's also an interesting window around the QCD scale. So why do I call that the QCD scale? Well, you'll notice it's actually the solar mass scale in primordial black hole mass. But solar mass black holes, that corresponds to the mass of the horizon at the time that the QCD phase transition takes place. So in the early universe, at temperatures of order 100 MeV, QCD goes from being free to being confined. And at that point, the number of relativistic degrees of freedom changes abruptly, and effectively the speed of sound changes. So it gets much easier to form black holes at that moment. So in a lot of models that actually make primordial black holes, you expect a little bump in the mass distribution around the solar mass scale, which is interesting for lots of reasons. We might know of some other objects around the solar mass scale. But in particular, it's not really clear whether some of the bounds here are really robust. So there's a lot of potential primordial black hole dark matter candidates in this region. Now, that said, the most interesting territory for the field for the last 5 years or so has really been that open window, which has gotten this name of the asteroid mass window. It's not actually really asteroid mass. Most asteroids are quite a bit lighter than this range, but that's what I'll call it for the purposes of this talk. So the challenge, if we want to rule out black holes or compact objects as a dark matter candidate, is really mostly on the low side, a little bit around the solar mass scale. We want to have really excellent probes at the solar mass scale for little bumps in the mass distribution, and we want to be able to probe black holes that are too light for these microlensing constraints to hold. Now, here's what I want to do in the rest of the talk. I'm going to tell you 3 little stories. First, I want to tell you about how the solar system can actually be used as a black hole detector, and how, in fact, it has sensitivity to this asteroid mass window that has been open for the last 10 years. Number two, at the higher mass end, I'm going to show you that, in fact, more massive black holes, 1 to 10 solar masses, can actually exchange pretty efficiently into stellar binaries, and you can find them that way. You can actually constrain black holes and some particle physics this way. And finally, I'll show you some brand new results, still to be published, taking advantage of a technique called femtolensing to actually probe the asteroid mass range. And I'm actually going to show you some fresh constraints based on the 700 gigabytes of data currently sitting on my laptop. So let's get to it. I want to give you a little bit of background about how dynamical probes work in general, because they kind of underlie the whole game here. So what are dynamical probes of dark matter? The underlying idea for dynamical probes of primordial black holes is that for a fixed dispersion, for a fixed velocity dispersion in a dark matter halo, the effective temperature of the medium is set by the mass. Right? If I give you a gas and I tell you its velocity, you can tell me its temperature. Now, if you have a stellar fluid, the mass of the particles in that stellar fluid is of order solar mass. So if you now try to invoke black holes as a dark matter candidate that are much heavier than stars, well, now that fluid is going to have a much higher temperature because its velocity is set by the same gravitational potential. So you have two fluids. One of them is very hot, one of them is much colder. They're in thermal contact gravitationally, and so you're going to effectively heat up the stellar fluid. So this is actually how some of the first constraints on dark matter of any kind were set. Like, there are actually papers in the late 60s and 70s thinking about constraining the mass of non-luminous matter by excess heating if it's made of a bunch of these newly hypothesized black holes. Now, a lot of the constraints that were developed with this method are really only effective for quite heavy objects. So if you're talking about black holes, hundreds of solar masses, those are pretty effectively ruled out by these dynamical bounds. As you go down towards 10 solar masses, 1 solar mass, this becomes a lot harder. So one opportunity to improve on these dynamical bounds is to think about binaries, individual binary systems, as behaving a lot like detectors. So yesterday I talked a lot about particle detectors, about looking for small excitations produced by dark matter coming through a sensitive system. Well, now I want to think about binary systems as actually being detector systems. So instead of using atoms and looking for the ionization of atoms, I want to look at a binary system and think about what happens to the parameters of that binary. So instead of ionization, for example, I can now disrupt the binary system. Now, if you look back over here, you will see that dynamical probes live on the far right side of the plot, again at sort of 100 solar masses, but there's a lot of other opportunities to bring that to lower masses. So let me just classify for you a few things that you could do with binary systems as a particle detector. One is disruption, right? The ionization. That's the sort of the simplest thing you can do with this heating effect. That's been done pretty well. You could also look at just softening. You could say, if I have this heating of the stellar fluid, can I just perturb binaries to make them expand a little bit? And will I change the distribution of binary separations in a way that is observable? To do that well, you need to know the initial distribution of binary separations, which is really hard. So maybe you can do this a little bit. It's sort of tricky. Maybe you could take advantage of hardening, the opposite process of softening. So I just have been saying this whole time that the dark matter fluid in this case is hotter than the stellar fluid, so you would expect to give energy to the binary, pull it apart, soften it. There's actually also a regime where if the dark matter particle is lighter than the elements of the binary, than the stars, you could take energy from them. So that's actually interesting, for example, for the asteroid mass range, where the dark matter particle is much lighter than stars you would find in a binary. So maybe you could shrink binaries a little bit. That turns out to be tricky. I can explain more if you ask me later. Another opportunity is capture. So binary systems are not particularly simple once you have a third object in the mix, because now you have chaotic three-body dynamics. So you can imagine a scenario where a black hole comes in, gets captured into the binary. They make a triple system. Or you could have an exchange process where the black hole kicks out one of the members of the binary and replaces it. Those haven't been studied. You could also have just transient perturbations. If you monitor a binary really well, maybe you could just see a small deviation from its well-established parameters. So what I want to do for about 2/3 of the rest of the talk is just focus on what we can do to get more out of binaries. And I'm going to highlight two of these. I'm going to focus first on the transient perturbations and then come back to dynamical exchange and capture. So let's start with the transient perturbations. And let's start with the binary, or that is to say, the system that is closest to home, solar system. So what I want to ask here is, can we actually use the solar system as a black hole detector? And the intuition here comes back to thinking about binary systems or arbitrary stellar systems as being like particle detectors. Right? If I just think about looking for individual scatters, well, the limit here is going to be the flux. Black holes are very, very heavy. We know how abundant the dark matter is. So if all the dark matter is made of black holes, they must be rare. I can quantify that for you. So for example, if dark matter is made of Planck scale black holes, the lightest black holes that we could accommodate, then we would expect about a flux of 1 per year per square meter. So if you like, it's laboratory scale. Right? If you have a football stadium, you'd expect about 3 of them to go through a football stadium per day. So you could build an experiment for that. But if I have asteroid mass black holes, now the number density is much, much lower. I'm talking about 1 per year per square AU. So I need a detector the size of the solar system. Now the solar system actually is a detector thanks to what we call ephemerides. I thought it was a Greek hero at first. It's not. Ephemerides are what we call precision records of the locations of objects in the solar system. And this is actually something that we as a species have been doing for a very long time. Although we've gotten considerably better at it in the last century. So what I want to ask here is, could ephemerides, could these records of positions of objects in the solar system actually record evidence of a black hole encounter with the solar system that perturbed planets or other objects? So we actually have really, really good measurements of positions in the solar system. Maybe the easiest example is this, and no, with apologies to Obi-Wan, that actually is the moon. So this is actually one of the first precision measurements we had in the solar system. That's lunar laser ranging. So we can measure the distance from the Earth to the moon with a precision of order centimeters. Shockingly, we can actually do almost as well for the distance between Earth and Mars. I did not believe this at first. But because we have orbiters and rovers on Mars, and we can do very effective radio Doppler, we can actually measure the Earth-Mars distance to a precision of order 10 centimeters, and we've been at that precision for at least 20 years or so. That's a really good baseline for looking for small perturbations. So let's now just calculate, naively, what would happen if we had a black hole flyby through the inner solar system. What would it do to that distance measurement? Well, predicting the motions of objects in the solar system is a very hard business. There are lots of objects to keep track of. I want to start by just simplifying. Rather than using these really, really complicated models, I want to just start with a simple toy model just to assess the size of those perturbations. So here's what I want to do. Let's say we take 2 simulations, both toy model, laptop scale simulations, one without the black hole flyby, one with the black hole flyby. And I want to look for differences in the object positions between those 2 simulations. Now, both of those simulations, the orange, the simple model in this cartoon, might be wildly off from the real data. But as long as I only care about the differential in the distances that's induced by the flyby, I can use this toy model. So that's what I'm going to do. I'm going to try to measure this delta R, this change in the location of an object, and I'm going to hope that that delta R is similar between the simple model and the full complex reference simulation. Let's do it in a few layers of complexity. So the first layer, I want to just do a back-of-the-envelope analytical approximation for you. The impulse approximation. So if I have an object that flies by quickly, I can write down the gravitational force at any instant. I can just do an integral. So let's say that a black hole passes by Mars. It has some velocity, some impact parameter. I can write down the change in velocity imparted to Mars by that encounter. And you can see that it scales like 1 over impact parameter, and it scales like the mass of the black hole. So far, so good. 1 over velocity. Now, the change in the actual distance to Mars, or position of Mars, is going to go like that delta V, that change in velocity, times the time that we wait. So let's say we have some precision on the position of Mars, some sigma r. And now if I want to have an event that is measurable, I need to have an object come within some maximum impact parameter, right? So it has a large enough effect so that I can see delta r go above sigma r in my observing time. You can do a very simple algebraic estimate and conclude that if black holes are the dark matter in the middle of the asteroid mass range, you would get about 1 observable event every 26 years. Interesting number, considering that we have 20 years of data. So the next layer here is to use simple laptop scale simulations. So a great student of mine ran these simulations on his computer with a simplified model of the solar system. It includes all the planets. It includes a couple of the larger asteroids in the solar system. It doesn't include the 2 million asteroids that the reference quality simulations track. What he showed, again back to this cartoon, is that in fact you can measure the change in position of the planets between the base case and the case with the black hole injected. And the results actually match the impulse calculation really well. So here, I'm going to zoom in a little bit for you. This is a profile in time of the change in distance to each of several planets in the solar system. And you can see that the impulse approximation predicts this sort of simple linear growth. That ends up being roughly the envelope for these more complicated oscillatory features. But the orders of magnitude are pretty well predicted. So far, everything looks consistent, and in particular, we can get perturbations that are at the meter scale where we can actually see them on the time scale of our data taking. Now, we can actually do a little better than that because there's very particular frequency space structure associated with these perturbations. If you looked at that picture, you saw these wiggles looked very regular. Turns out it's pretty easy to understand where the peaks are in the power spectrum. So if you imagine looking at many, many orbits of these planets, looking at many, many cycles, you could actually build up the signal-to-noise ratio and beat down that sigma r a little further. That's going to be important in a moment. So here's what you can actually do with it. Here, I am showing you as a function of black hole mass, as all the dark matter, the rate of detectable events. There are 3 different assumptions here on noise reduction. So again, I have not attempted to do here the full, gigantic reference quality simulation to compare with data. So I can't say exactly how much noise there is, what exactly the backgrounds are. What I can say though is that if I only look at Mars, if I ignore correlations with anything else, I'm doing the simplest possible analysis, and I assume that I have some kind of matched filter analysis that can improve my signal to noise by a certain ratio, then I get, in the pessimistic case, the green shaded region. In the optimistic case, if I do as well as LIGO does with their matched filter, then I can get the blue curve. So that means in the LIGO-like scenario, we actually see of order 10 black hole perturbations if they're at the bottom of the asteroid mass range. Now, this is just a projection on how many events you would expect to see. It is not a constraint. In order to claim a constraint, you have to actually go through that archival data very, very carefully. You have to actually do full reference quality simulations with primordial black holes injected and see exactly what the templates look like. So I am not claiming that this already sets a constraint, but I am claiming that the solar system is sensitive should we finish this analysis. Now, doing that full physics analysis, it just takes the reference models that have actually set the standards for ephemeris calculations to date in the solar system. So we actually have friends over at the Paris Observatory who are experts in simulating the solar system. And for a little while now, we've been in a back and forth trying to understand exactly what's necessary to drop primordial black holes into their enormous simulation that tracks 2 million objects, and to see if we can actually get templates that we can use to go through archival data. So this is a work in progress to actually get constraints, but the sensitivity is there. Now, I want to just mention that what would you do if you saw something? Right. My dream, I'm kind of a killjoy when it comes to black holes as dark matter. I want to show they're not there. So that means I'm hoping that we do this analysis and we find there are no perturbations that look like black holes. Of course, we might get unlucky, or lucky, and find a perturbation that sure looks like a primordial black hole hit the solar system. In that case, could you follow it up and actually determine whether it was a black hole or not? Well, that's a little out of my pay grade, because that's a very complicated observational astronomy question. And there are some people in the observational astronomy community who have now started to think about how you could do rapid follow-up to try to diagnose whether such an object actually passed through the solar system. This is a little tricky, though, because you don't know when you're going to see it. You might only see the perturbation after it's been a few years already, and so the object might have passed out of the solar system already. So I would say it's easiest as a tool for constraint. Discovery gets a little tricky, though there are potentially ways to follow up a candidate observation to see whether there is something not dark that produced that signal. I'm going to briefly point out there was some discussion on the archive a little while ago about whether the very fact that we have these ephemerides actually already tells you about primordial black holes as a dark matter candidate. There was a little argument about whether you could just use the fact that we know the mass of the sun pretty well to set limits on black holes as dark matter. Right? If we know the mass of the sun to less than 10 to the 18 grams, well, if black holes are the dark matter, then the mass in the inner solar system is going to be fluctuating over time. Poisson fluctuations as black holes enter and leave the solar system. So surely if we know the mass of the sun that precisely, we can rule out such a granular dark matter candidate. That turns out not to be the case. The reason it turns out not to be the case is that that solar effective mass is actually determined only at small radii. And in order to make this effective for probing black holes, you have to be able to say that you know the effective solar mass at a radius of 50 AU, which we do not. Okay. I will just mention that there has been some good follow-up work by careful simulators who have tried to understand, are there actually Poisson fluctuations in the ephemerides just from the fact that you have black holes coming in and going out of the solar system, effectively building on that Poisson fluctuation idea. They showed fairly conclusively that you do not see those Poisson fluctuations. They are, at least an order of magnitude below sensitivity. So you really need this kind of matched filter technique to reduce the noise level a little bit to bring out the signal. You can't do it just by looking at Poisson fluctuations. Okay. Finally, last word about the inner solar system. You might have thought that there's actually a bunch of objects that we measure really well, the ones that we put there. Right? There are a number of artificial satellites that we monitor with extraordinary precision. So GPS might come to mind. Right? We monitor the clocks on GPS satellites. If they were ever perturbed by a transiting black hole, surely they would register that effect. As it turns out, this sort of works. It works for a lower mass range. So the canonical asteroid mass window is above most of this. You can maybe get the very bottom of the asteroid mass window this way. And the reason is easy to understand. It's just that GPS satellites don't cover that much area. Right? The solar system itself, the inner solar system, is huge, multiple AU in radius. This is only tens of thousands of kilometers in radius as a network. So lighter black holes can be probed this way, but not really the canonical asteroid mass range. You might hope that you could do a little better with this future satellite. This is LISA, which is going to be a gravitational wave detector, million-kilometer arms. really, really good distance measuring precision, and there were some papers over the last 20 years claiming maybe you could detect compact objects this way. As it turns out, some more recent analyses have shown that you really can't quite get there. You really need about, you can only probe 100 times the dark matter density this way. But LISA will actually be able to probe primordial black hole formation scenarios from gravitational waves. So still a great instrument. Okay. Real quick recap on the solar system as a black hole detector. The solar system is a primordial black hole detector by virtue of very well characterized planetary orbits. That is, as it turns out, the most sensitive tool we have in the solar system. It has its best sensitivity in the asteroid mass range, and we can actually potentially draw a constraint or discovery with archival data very soon. And the thing I want to add here is that this is something that I was asked about a lot by non-physicists at one point or another. Like, could there be black holes in the solar system? And I would always say, no, that's probably not. That's kind of a silly idea. And I always thought the answer to the question would be boring. And it turns out it's not. So that was a really fun surprise for me. I didn't think this was going to work out as well as it did. Okay, that's the solar system. But the solar system is not the only system we get to use. And so now I want to turn to the dynamics of other systems. And in particular, I want to talk about exchange processes in other astrophysical systems, focusing on binaries. Here, the idea, back to the direct detection analogy, is to think about binary systems as paleodetectors. So, if you've heard of a paleodetector, the idea here is that if you want to see something that happens very rarely but has a low flux, what you need is a long exposure area or long exposure time. Right, so you could have a gigantic detector like the solar system, or you could just have a detector which has been sitting there for a very long time. In the direct detection case, that translates to rocks. Right, you dig up a rock that's been underground for 1 billion years, you see if there's been any scattering damage in the rock. For our purposes, the equivalent of a paleodetector rock is an astrophysical system, still, because they could accumulate black holes over time, over billions of years. So can you look for accumulated black holes? Well, the simplest thing you might think of here is capture. Right? If you have a binary, 3-body dynamics can lead the binary system, 1 and 2 in this picture, to capture this incoming black hole, number 3, so that the final state looks like this. You have a triple system, 3 objects. That turns out not to really work. And the reason it doesn't work is that even though you can compute the capture rate, even though you can figure out how often something gets captured and it happens at a decent clip, even though it's very messy, those captures are unstable. Those triple systems have 3-body interactions the whole time that they exist. And so the same dynamics that brought the system together that caused the capture will cause slow changes in the parameters of the system and eventually will cause an ejection, the time reversal of the capture process. You can actually compute the ejection rate. It's hard, but you can do it, or at least estimate it. And it turns out that for most astrophysical stellar binaries capturing objects that would be of interest for us, you really don't have long lifetimes at all. Captures are only going to last maybe 1 million years at most. So that's not really a great way to accumulate black holes. But dynamical exchange is different. So here the idea is not that you capture the incoming object into a triple system. The idea is that you actually kick out one of the objects that was originally in the binary. So now the binary is only the original object number 2 and the black hole. There's no longer a third object, there's no longer chaotic dynamics, that binary is stable. So this can accumulate over a long time. You could look for binaries of a star and a black hole. You can compute the exchange cross-section. As with the capture cross-section, it's very ugly. In fact, this version comes from Fitts numerical experiments that were performed back in the 90s. We actually had to redo these fits because they weren't done originally in the velocity regime you expect for dark matter. But given that, you can still write down the exchange rate as a function of this nasty cross-section. And you can just compute for various binary systems and black hole masses, what would you expect for the exchange rate, the rate at which a system is disrupted and replaced? Well, you'll notice here there are a few different curves corresponding to different binary systems. So let's look, for example, at curve D, the blue curve. That is a binary system which is separated by 10 AU, where the components have masses 10 solar mass each. And you can see this characteristic structure that you'll see in each of these curves. There's a peak in the exchange rate. That peak is essentially where the masses match, right? So you see that for the blue curve, that peak occurs roughly at 10 solar masses of primordial black hole mass, because it matches the solar mass, the stellar mass in the stellar system. The dot dashed lines versus the solid lines just reflect the fact that with the solid lines, you're assuming all of the dark matter is black holes. The dot dashed lines are taking reasonable bounds into account from the constraints I showed you before. So while there are caveats to those bounds, you really shouldn't expect to have an exchange rate higher than the dot dashed curve. And you'll notice that exchange rate is extremely low. On the vertical axis, these exchange rates are maybe 10 to the minus 10 per gigayear at best. Now, that is low indeed, but we have many, many binaries, and that changes the math. So in fact, as it turns out, if you actually compute the exchange rate for various kinds of systems, you can just ask yourself, is there any hope to see exchange into several kinds of binaries? So the first thought, because of that peak, you might wonder about asteroid mass binaries. Could you look for asteroid mass black holes that have exchanged into asteroid binaries? It turns out that doesn't really work. Exoplanetary systems, you could ask the same thing. Could I look for a dark exoplanet? You could. The rate turns out to again be too low. And then there are stellar binaries, where if you have black holes that are produced in association with the QCD transition, maybe those will exchange with a star. So if you compute the rates, for asteroids it's too low. For exoplanets, you just don't have enough exoplanetary systems to even begin to do the analysis. But for stellar binaries, there are actually already interesting hints that we may have seen such exchanged black holes. So let's talk about Gaia BH1. Gaia BH1 is a system discovered by the Gaia satellite. It is a black hole in a binary with a light star. The black hole is about 10 solar masses. The star is about 1 solar mass. They're separated by only an AU or so they're really close. Now what's weird about this is that because they are so close, and because this black hole is 10 solar masses, you can kind of walk the system back in time. The progenitor of that black hole, if it was a star, would have had to be so large at the end of its life that it would have encompassed the smaller star. Now that's not a problem. This happens often in stellar systems. But you would expect that elements from the heavy star would be sucked onto the small star. But you can look at the chemistry of the small star. It doesn't look like it has those heavy elements from a larger star. So this doesn't look like a system that formed in situ. It looks like a system where the black hole came later, or in principle the system contracted later. Now if you just compute the exchange rate that is required to explain the presence of this system, it turns out that you need an exchange rate that's a little bit higher than what you expect from the ordinary background black hole population. This is something that the Gaia collaboration actually computed, trying to ask, could you do it with black hole exchange? You need a couple more orders of magnitude. You need about 10 to the minus 7 per gigayear. You can actually do that with primordial black holes at the 10 solar mass scale. So in fact, if most of the dark matter, as much as you can have, is at the solar mass scale, this actually matches pretty well. You can produce systems like Gaia BH1 in the amount that they are seen, where we otherwise don't know how to form them. Okay, that's an interesting hint. Can you do anything else with exchange besides these kinds of puzzles? Well, it turns out you can actually use them to set constraints on particle dark matter physics. So here I've been talking about primordial black holes. It is black holes that were produced in the early universe. You can produce those black holes also from having dark matter that cools down and clumps and makes black holes. So that actually turns out to be a perfect setting for exchanges, and you can actually get unreasonably large exchange rates that you can immediately rule out on the same basis. So, for example, The best benchmark here is atomic dark matter. This is a class of dissipative dark matter models where you have a dark proton and a dark electron that are talking to each other via a dark photon. So this is sort of think of it kind of like a copy of the standard model baryons, but without any nuclear physics. So just a inert proton and electron, no nuclear physics. Now, you can actually do full-scale simulations of what the galaxy looks like with this atomic dark matter, which, because it has that photon, it can cool. It can form structures that kind of look like our galaxy. So on the left here is what the actual galaxy looks like in the simulation. That's just baryons. On the right is what the atomic dark matter component looks like. You can see it essentially forms its own galactic structures. And those structures are essentially co-rotating with our galaxy. The relative velocities are quite small. When you have gravitational interactions and a low relative velocity, that is the key to large cross-sections. Think about gravitational focusing, right? Something that's very slow but very far away will still be able to be attracted to something that has a long-range gravitational pull. So, what if we have some atomic dark matter in the Milky Way? Would we get black holes? Would we get exchanges? To the first question, we would absolutely get black holes because atomic dark matter cools really effectively. So you can see actually in the simulation, they've written ADM clumps. Clumps here is just the dark matter will clump and form structures that look like they're going to make black holes. The simulation can't resolve it, but you can basically assume that all the dark matter that clumps this way makes black holes. So the atomic dark matter does make black holes. They're slow moving with respect to the stars in the galaxy. And you can compute the exchange rate. This is a plot that a student sent to me just a few days ago. These are constraints on actual atomic dark matter parameter space. So on the horizontal axis, you have the coupling of the dark photon, the equivalent of our fine structure constant. On the vertical axis is the dark proton mass. And this has a fixed relation between dark proton and dark electron masses. And what the colored contours are showing you is that exchange rate in the same units that I was showing you for Gaia BH1. So what we actually want to match, if we want to just explain Gaia BH1, we need an exchange rate of 10 to the minus 7 in these units. If we're much higher than that, then we can actually set a constraint because we don't see systems that have had black holes exchanged into them that often. And you can see we can get enormously high exchange rates because of the low velocities and high densities of the atomic dark matter. So for example, at low dark electron mass with a dark fine structure constant similar to ours, we would have an exchange rate that's several orders of magnitude beyond what we actually see. So we can actually even use binaries to set constraints on particle physics that is the progenitor of these black holes. Okay. I want to move now to the last mass range that I want to discuss. Are there any questions on the first two pieces before I move on?
For the asteroid mass black holes, two questions. If they're coming in 1 per square AU per year over many, many years, they will occasionally hit a planet. Should we see some effect from that? And two, if we're using ephemerides to detect the things in the first place, won't we just find a whole lot of foreground of normal asteroids?
Great. To the first question, would we see something associated with black hole impacts on planets? The answer is that in the asteroid mass range, those are unfortunately too rare for us to see them. If you take the bottom of the asteroid mass range, you would expect that about 1 would pass through Earth through its entire history. Just because the cross-section is so small.
But it's cool. What would it look like? If it
Yeah, I know. It is cool. So actually, I'll tell you, I computed this, and I was telling Glenn yesterday, I had a substantial argument with someone about whether I was right or not, and then some hydrodynamical simulations showed I was right, so I was very happy. So indeed, you would actually end up with what you would see on the surface looks like a crater, and then there would be a channel of broken rock going all the way through the Earth. It would not be deflected at all. Of course, Earth shifts over time, so you'd really have just like these sticks of broken rock. But I actually did spend some time thinking at one point about could you use like ground penetrating radar to go and look for these kinds of channels. It turns out not to be a competitive constraint, but yeah, people have actually simulated what it would look like to have black hole impacts on like Jupiter's moons, for example, where it might be easier to actually make the distinction. Okay.
Asteroid foreground.
Oh, I'm sorry, asteroid foreground. Yes. So if I'm looking for asteroid mass objects in the solar system, there are plenty of asteroids in the solar system. How do I know I'm not seeing an asteroid? Well, because first of all, you should only expect the constraint I was telling you about to work in the upper half of the asteroid mass range. And in that upper half of the asteroid mass range, there are very, very few objects in the solar system that are that heavy. All of the asteroids that we know of there are only, like I can count them on one hand, the number that are that heavy. Most of them are like 10 orders of magnitude lighter. Now, can I guarantee that we haven't missed something that is, I can't guarantee it, but that's the whole point of observational follow-up, right? So if there's something that's bound to the solar system, we have a good chance of finding it.
So if we're talking Vesta mass, then yeah.
So Vesta has to be included in the simulations for this to make sense.
Okay.
Yeah.
And are you only looking at things that are in the inner solar system, or how about outer solar system?
Yeah, so outer solar system would be great. We just don't have the same kind of measurement precision on outer. Oh, I'm sorry. I'll repeat the question. The question was, do we look only at the inner solar system versus outer solar system? Outer solar system would be great. We just don't have the same measurement precision. So in principle, and there are, I think, lots of reasons to do precision measurements of the distances to outer planets. But for now, the archival data is really limited to the inner solar system. Let's move on, and we can have more questions later. I want to tell you about some really recent progress in probing the asteroid mass range. And I really mean probing asteroid masses today. Here, the idea is based on a technique called femtolensing. And to explain what femtolensing is, I first want to explain microlensing. So if you look at the constraint plot again, you will see that there is this big blue region that's labeled microlensing. And you'll see that it actually stops at smaller masses, right? So it doesn't extend into the asteroid mass range. Well, what's going on here? What is microlensing? You have some light source, a star, let's say, and you have an observer on Earth. Ordinarily, you would just see a light ray coming from source to observer. If you have a lens, a black hole in the middle, light can bend around that lens and make it to the observer. So you effectively see more light rays in this configuration than you saw before. That means that as the object transits your line of sight, you will see a brief magnification effect. You'll see an increased brightness while it's there. So this is an example light curve of a microlensing event where you're seeing the intensity as a function of time. You see this little microlensing bump. This is called photometric microlensing. Why doesn't this work in the asteroid mass range? There are actually two distinct reasons. One is that the sources are not sufficiently point-like. The lenses are so small that, in fact, it looks more like this. Where, yeah, okay, you're getting some microlensing enhancement of that little dot at the edge of the giant light source, but you also have plenty of light rays that are just doing that and not getting lensed at all. So the magnification effect is much, much reduced. The other issue is that the light isn't ray-like. You are actually in the wave optics regime, and that is because the physical size of a black hole is related linearly to its mass. And in the asteroid mass range, I love this number. It turns out that in the middle of the asteroid mass range, the actual radius of a black hole is comparable to a hydrogen atom. So yes, everything I was telling you about perturbing solar system orbits, doing that with hydrogen atom-sized objects. But this also means that the wavelengths of light that are often used for these microlensing surveys are not sufficiently short to be in the ray optics regime. And so there are wave optics effects that suppress the magnification effect. Now, there is another way that you could think about doing this. You could think about trying to go a little bit further just by overcoming these two issues independently. Right? You could use shorter wavelengths and smaller sources. So this is actually an idea that has appeared in literature. Some smart folks realized you could actually use X-ray telescopes, shorter wavelengths, and you could use X-ray sources, which are compact objects like neutron stars, to overcome both of those challenges and actually be able to see photometric bumps. The issue is this projection plot is unfortunately sort of impractical. And the reason it's impractical is actually because the assumptions being made here to even achieve these scalings are quite optimistic, unfortunately. So, for example, the curve here that says NICER 60 days. NICER is a real X-ray telescope. It exists. In principle, it could do a 60-day observing campaign. I don't think it has ever done 60 days in combination across all the sources it's ever looked at. So that's already a tall ask. And the other curves on here, StrobeX and X mu, those are future experiments which StrobeX may or may not happen. X mu almost certainly won't happen. What is actually limiting this at the end of the day is that there's only a certain number of sources that you can use for this analysis, because most of the sources that would be good candidates for this are intrinsically variable. They have brightness fluctuations. So if you are looking for a photometric microlensing bump, you have to have a source that is very flat. Now, unfortunately, that means you can only use a very small portion of the archival data. So in the existing NICER data set, across all existing NICER data, they're able to get that red wedge there, right? But there is another way, and that's femtolensing. So what is femtolensing? Femtolensing is when you're in the wave optics regime and you have interference fringes. So instead of just having rays that bend around the lens, you have plane waves that encounter the lens that cause these diffraction wave fronts to go out. And the separation between peaks and troughs in those interference fringes will be different for each color, right, for each wavelength. That's what I've tried to draw here, right, so that you can see the red fringes are more spaced than the blue fringes. What that means in practice is that if you plot the intensity that you see as a function of color, right, as a function of frequency, the spectrum, that is actually going to change during the lensing event. So at first, if it were not in the line of sight, we're going to have some background spectrum. I'm going to say that it's maybe flat in this parameter space. It doesn't have to be. But now there's going to be a transient fluctuation where the spectrum is suddenly going to look wiggly because now you're seeing peaks and troughs at different frequencies. Then you wait another moment, and the event stops. We're back to unlensed. What is really nice about femtolensing is that you don't have to worry about that intrinsic source variability, because there is basically nothing that mimics this kind of momentary fluctuation. So, what data can we use in principle to do this test? Well, there are three experiments I would point to. One is RXTE, or Rossi. This was an X-ray telescope that was in service between 1995 and 2012. NICER is the sort of modern version of that instrument, although a smaller effective area. It's been active since 2017. And there is a future instrument called Athena, which is proposed to launch in about 10 years. So those three are sort of the technological arc I want to look at. And now I can show you what you actually get. Because again, for NICER and RXTE, those experiments already have vast amounts of archival data. So what I did is I actually implemented a search for femtolensing events, for these spectral fluctuations, with a timescale corresponding to a transit. And what I found, I'll explain it curve by curve, starting with RXTE, the dashed green curve. What I first found disappointed me greatly, because that dashed green curve is what Rossi would give you if it had better time resolution. RXTE is the Rossi X-ray timing experiment. One of the big features of this instrument was its time resolution. But at that time, time resolution was, it meant 16-second bins. The timescales for these transits are order 1 second. So that's not good enough. You really can't get anything out of Rossi. The solid green curve, that's NICER. That is archival NICER data that actually exists with an actual real search. And you will see it actually crosses below the F equals 1 line, the line where you're probing dark matter as asteroid mass primordial black holes. So this is actually setting a non-trivial constraint. And I have not finished optimizing the background projection. So in principle, it could do a little better. I anticipate that NICER in principle would set a bound that looks kind of like this. If I can get the background rejection a little bit better, we could do maybe about a factor of 5 to an order of magnitude in there. And then the purple curve is what Athena would do if it has an observing program that is similar to NICER. So here the idea is Athena just has a gigantic effective area, and it's got a really nice spectral resolution, really great timing resolution. It's basically the perfect instrument for this. It will basically close off a huge portion of this mass window. Now the little portion at the left here, that is actually something where other probes are starting to get competitive. Evaporation bounds are extending a little bit higher in mass. These local solar system satellite tests can get a little bit higher than the evaporation bounds. So we could actually, in principle, close the asteroid mass range entirely using this in combination with some other probes that are known to work. So I find that very exciting as someone who's tried to kill primordial black holes as a dark matter candidate for many years at this point. I want to just summarize where we stand with primordial black holes and more generally compact objects as a dark matter candidate. So again, mainly we are looking at the asteroid mass range now. There are a couple of other places that we might want to look. But if you were at my talk yesterday, I showed this paper from a while ago about WIMPs as an example of how sentiment has changed in the field. We had this sort of moment of truth reckoning. The experiments turned on. What are we going to see? We are now in a similar position for primordial black holes as a dark matter candidate, where we really should be able to say something definitive in the next few years, or at least have a plan to use data that is already coming in the next few years, that makes them a viable dark matter candidate or not. Now, if they are not the dark matter, that does not mean they aren't interesting. They are fascinating objects. They can still do a lot for you. They can seed supermassive black holes. There is great interest right now in little red dots in the early massive galaxies that James Webb Space Telescope has seen. They can be probes of dense dark matter environments in really interesting ways. They can be probes of evaporation. If you want to see a black hole evaporating, you must have primordial black holes, and I certainly hope that we have black holes evaporating. I once said to someone who asked, if I could ask God for one experimental instrument, it would be an evaporating black hole. So there's still lots that primordial black holes can do for you, even if they are not dark matter. But what I view as the end game applies to their status as a dark matter candidate. I think that we are now at the cusp where we will indeed be able to flush them out of any remaining hiding spots, where we can probe them in the solar system, we can probe them in other astrophysical stellar systems, and we can actually get real constraints very soon from existing X-ray data. I'll stop it there. Have fun.
Go ahead. The microphone. Thank you for the really fascinating, great talk. You two things. One, you talked about closing the asteroid window with the femtolensing. That does it for PBHs, but it wouldn't do it for bigger compact objects. Right? Okay,
good. So for bigger compact objects, it would work a little bit for bigger compact objects. It depends on exactly what frequencies you have available, because again, you do depend on being in the wave-like regime. So that it's also worth saying that the evaporation bounds are totally irrelevant for compact objects that are not black holes. So yes, there is absolutely freedom for other compact object dark matter at those light masses.
And as you said, the evaporation bounds wouldn't apply if black holes don't evaporate.
Indeed. Right, I've actually spent a lot of time thinking about what you can do for non-evaporating black holes. And I thought for quite some time about what I view as the nightmare scenario, which is relics, black hole remnants. So if you have something that evaporates down to the Planck scale and then stops evaporating, now you're in trouble, because you have what effectively looks like particle dark matter at the Planck scale with no non-gravitational coupling. So that's horrible, right? So what do you do in that scenario? Well, in that scenario, you actually get lucky. There is a way in principle experimentally to probe them in the future. But if you happen to have, for example, there are arguments these days about memory-burdened black holes. And I have lots of opinions about the memory-burden framework, but it would allow you in principle to have even black holes that sit in the otherwise evaporation-limited regime stably at masses that we could not probe. That's a challenge.
maybe connected with Glenn's question. How about, what if we produce primordial black holes with different mass ranges? Well, from the theory, like production mechanism side, I guess it can be quite awkward to do so. But if you were to rule out primordial black holes with the asteroid like range, would we rule out primordial black holes as dark matter candidate, or could we still, have
Good. Okay.
a plateau?
Yeah, let me go back to this plot. So here, the statement is basically, if we didn't limit ourselves to that open window, could we find? I mean, obviously, from this picture, it kind of looks like there's no other room, maybe apart from the low mass, non-evaporating case. But you could still ask, what if you aren't committed to having a single black hole mass? In general, you would expect some distribution of masses. Could you draw some wiggly line that looks like this, right? And the answer is that gives you a little bit of extra freedom, but it doesn't give you that much additional freedom. This turns out to be a kind of a fun math problem. You can ask, what is the distribution of black hole masses that maximizes the allowed amount of dark matter given the constraints? And you can actually solve it as a problem in convex optimization. I did this exercise when I was a grad student. And what you end up finding is that in most cases, if you close the asteroid mass window like a little bit below 1, you have to go a little bit further down below 1, that's enough to shut off black holes as a dark matter candidate, period, with full freedom in the mass function.
So you showed two oscillatory plots. One was the distance between Earth and Mars, and it seemed to oscillate. And I wanted to check if the frequency scale was set by the frequency of the Earth and Mars's orbit.
Yes, it is.
Okay.
It absolutely is.
Okay, good. I think that'll make a nice qualifier problem. So something to think about. But then the other one was more puzzling. In the microlensing, you showed oscillations too, and I thought that was going to be like set by the, radius of the black hole. But
yes, actually.
Oh, it is set by the radius of the black hole.
Yes. So the fact that you were in the it's dependent on the size of the black hole. It is not uniquely dependent on the size of the black hole. So you were in the wave optics limit only if the black hole mass is small enough that the size is smaller than the wavelength. Once you're much smaller than the wavelength, the radius of the black hole no longer really matters. But the mass, of course, still enters and it's linearly related to the mass. Yeah.
Well, that's what I was worried about. It sounded like
You were in this extreme limit where it was much smaller than the wavelength, right? You said it's about the size of a hydrogen atom, and the wavelength of light is, 10 to the 4 times bigger than that. So
we're in the X-ray regime. So
you're looking at X-rays. Ah.
Yeah. So that's why. So KeV, we're talking about 1,000 times shorter wavelength than visible light.
Okay.
So indeed, this only works. That's why. If you look at the actual this constraint plot, you'll see it only works in a fairly narrow window. The reason it only works in that narrow window is because you have a certain spectrum where you can match where the black hole is to the black hole mass to the portion of the spectrum that you're seeing. I think that the plot that I showed you here is in some sense deceptive because I was lazy in my cartoon and I showed it wiggling over the whole frequency range. Mm-hmm. Really, you only get a wiggle where you have the matching.
Yeah. Okay. Yeah. Perfect. Thank you.
Thank you for the talk. You made a comment about the QCD phase transition. We understand pretty well, people work very hard to understand how the number of degree of freedom changed, really hard work, lattice calculation, everything. What is the comment that you were connecting to black hole production? Can you clarify that? Maybe you were too quick.
Sure. So the idea here is not that the phase transition itself seeds black hole formation. It's just that if you have perturbations that are collapsing, the rate at which they collapse depends on the pressure. And the pressure itself changes when the QCD crossover happens. So I would say that it's less that you have to be lucky and more that generically for a set of perturbations that give you black holes across different scales, you always expect an enhancement at the mass scale that corresponds to the horizon mass at the QCD transition. Yeah.
I just wanted to ask sort of a non-technical question, which is like you express sort of a general hope that primordial black holes are not actually dark matter. And I was wondering why that is, and if you have a different hope that is, for something else, and why that would be.
I should say that being generically interested in what dark matter is, if nature provides me with evidence for primordial black holes, I will be thrilled and delighted, of course. Are you listening? But what I should say is that, first of all, if I had to guess, I would guess that black holes are not the dark matter from a theory standpoint, because there's some missing ingredients here. It's not maybe as minimal as it seems, because although in principle you can do it without having any additional degrees of freedom besides the inflaton, you still need some kind of tuning to get black holes at all without massively overclosing the universe. And you also have no reason to expect that the amount of dark matter in black holes is at all related to the abundance of baryons. Right? This is sort of the major puzzle that if you ask me, why do I imagine that dark matter has any non-gravitational interactions at all, my best answer to you is the abundance is really similar to the baryon abundance. How did that happen, if not by some non-gravitational coupling? So this is always the problem with any gravitational production mechanism for dark matter. There must be a way to explain that abundance, and this is effectively a gravitational dark matter production mechanism. There's not really a clear built-in way to account for the abundance of dark matter. So I would be excited, but I would be confused. I would have follow-up questions.
Okay, if there's no further questions, let's thank Ben again.